There we go. Okay. So stacks and queues. I have tons of videos on this because we also covered them in 302 and previous two semesters. And there's tons of information online. They're very basic concepts. So I think I can pretty much tell them to you in like 5 minutes both. But I'm going to try to go a little bit beyond that and show you kind of like the nitty gritty of them. A little bit about like analysis of what they're useful for. I want to try to give you like a bigger picture and, you know, really kind of stretch them out to make sure that you understand them pretty well and their usages and eventually how they're going to lead into 302, which is the sort of the next step of the CS degree. So we got to pick one to start. So I'm just going to go ahead and pick I don't know. Like, I'm inclined to pick stack because it's a different one, but queue is kind of easy. So I'm going to go with queue. Yeah, let's go with queue first. Unless anybody wants to do stack first. I feel like the queue is going to be the most straightforward one. So get the easy stuff out of the way. So, and by the way, reminder, if you are redeeming points, make sure you send me your name, your Twitch ID, and your class, 202 or 302. Okay? So, what is a queue? A queue is like what the British people say when we say like get in line, right? So like when you go to the supermarket, this is you on the supermarket, and you go to that supermarket, and there's a lot of people that are waiting to pay because, you know, you're grocery stores. And that's pre-COVID days, I guess, because nowadays we just buy everything online, right? But yeah, so you go to the supermarket and you get there. You can send it either way, Discord or email or Canvas, doesn't matter. Just make sure you send it to me at some point before like 7 so that I can just get everybody done at once. Okay, so like you're walking around and, you know, you're trying to pay, or maybe like, let's put something more realistic. This is they're releasing a new GPU, the 3090 like Ti or something, and you're all standing in, you know, you're standing in line because you want to get it, right? And so you get there and you see a bunch of people in the line, right? And so in theory, unless some shady stuff happened, the person in the front of the line has been waiting the longest because he got there first, right? And so you're going to go in and you're not just going to like skip to the beginning and like cut these people and then start a fight and then like, you know, bad things happen. You're going to be ordered and go to the back of the line, right? And if somebody comes after you, they're going to go to the back of the line. And eventually, when they finally open up whatever store this is and they allow people to walk in and get their GPUs, the person at the front is going to have that priority to get the GPU first, right? And if they have only like 4 GPUs, then you're lucky because you're the 4th person in line. So in theory, these 4 people should get the GPU, and then this person is going to go home sad and end up having to pay a scalper to get that GPU, right? So, or maybe they'll go somewhere else and try to get it. So that's the most basic form of like waiting in line, right? And that's literally what the queue is. A queue is a data structure that allows you to store information that you want to have, you know, first in, first out. So let's talk about that. First in, first out. FIFO. The concept of first in, first out is that the first person that gets into a wait is the first person to be served, right? Because it's been waiting the longest. If you come into the line and there's people before you, they should get served first in a good queue, right? And I'm really trying to find out what else to say, but I think most of you understand that basic concept, so we can kind of move on to actually how do you implement this. Now, whereas in the past, you know, in 202, you know, I talk about arrays or I talk about a linked list, then you implement these things in terms of code. When you talk about something like a stack or a queue, I'm not talking about any specific form of implementation. In fact, there's tons of ways to implement a queue. The 2 main ways that we're going to be looking at is implementing them using an array and also implement them using a linked list. And I'm going to talk about the pros and cons of using either or the systems. But from like the meta point of view, queues themselves are a concept and they don't specify how they're implemented. It's not like a linked list where like pointers are involved and you gotta like have a node, a previous, and next pointer. No, none of that is we're talking about. We're talking just about a concept. And that's basically what 302 is. You talk about these concepts like these data structures, and you're not talking about implementation specifics. You're just talking about the concept in general. It is up to you, the programmer, to decide on the programming language and then actually implement this in reality. And how you do that is up to you. And there's right ways to do it and there's wrong ways to do it. And by wrong, I'm saying not like you're going to get the wrong output and someone's going to cut the line. I'm saying in terms of speed and time. So in 302, you're going to be looking at time complexity and space complexity in terms of asymptotic complexity is the name. And what that really implies is that it's not enough to just code that something works. You care that it works efficiently, both in terms of speed. So like if you code something like you're going to code sorting in 302, and so far you probably know from 135 bubble sort. It's not the fastest of the sorting algorithms, but it gets the job done. It ain't much, but it gets done, right? And so basically, at the level that you're at right now, it doesn't matter. You just want to get things done. But pretty soon it's going to be like, it's not enough to get things done. You want to get things done quickly. And the other side of the coin, but not as important nowadays, is space-wise. You don't want it to take a lot of space. You could have this like super, super, super fast algorithm that's going to like, solve all of the world's problems in like 2 seconds, but it requires like an insane amount of like space to run. And not all the space in the world is enough to run it. Pretty useless too, right? So there's always a balance between space and time. And those are the two big things that you're always seeking balance of. Most algorithms are biased in one way or the other. Something that's really fast in terms of time can be really slow in terms of space. And by that, I'm saying it takes a lot of space. Or vice versa. Something that takes a lot of space, but takes very little time because it's really fast. So I think I said the same thing twice. But the other algorithm is like it takes very little space, but it takes a lot of time. Quick example, just to give you an idea. Think about encryption. Or not encryption, sorry, compression. So if you're trying to compress like a zip file, you take a big file and you compress it as much as you can. You make it smaller so it takes less space. But if you try to access the file, it has to decompress it first. That takes a lot of time. And so it slows it down, right? So you got less space, but it takes longer time to run. On the other side of the coin, there's something known as hashing, which you'll learn in 302, which allows you to access items really, 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 really fast, but it takes a ton of space, like a ton of space. Well, hashing itself doesn't take a ton of space, but the concept behind it, which is direct access tables, do. So they're just two quick examples, okay? So stacks and queues are in the same world that how you implement them is going to affect that. There are ways that you can implement a stack and a queue that take less space and ways that you really shouldn't because they take more space, okay? So from an implementation perspective, before I go in there, let me tell you some terminology that comes in when you're talking about queues. So when you're talking about queues, you have two main operations. So think about data, object-oriented programming, the name of the game in this class, and how we have the concept of encapsulation, right? That we want to take the data and the operations on that data, right? So in this case, the data is whatever you're storing in the queue. So it doesn't matter, numbers, people, whatever. But what matters is what operations you can do in that data. And there are two main operations that you do in a queue. And that is going to be to enqueue something and to dequeue something. In general, and this is something for 302, is that there are three main things that you care about with algorithms. And that's inserting into it, deleted or removal from it, and access. However, delete is more of a combination of access and delete because you have to access or you have to find something to be able to then delete it usually, right? So, yeah. So when you're talking about your enqueue, that's your insertion. So when you insert something into a queue, when you get in the line, that's called to enqueue. So I don't know, think about enter queue if enqueue doesn't make sense as a word to you. Dequeue is your removal, but it kind of is your access too, because the only way that you can get something out of a queue, and now I'm talking about like the purest form of a queue, because I mean, you code this however you want to code it in a way. So if you want to do some weird thing where you can actually cut the line with a secret code, that's on you, but that's like not like the most basic pure version of a queue, which is what I'm talking about. So the two operations, just enqueue and dequeue, okay? In terms of other things that are relevant to a queue, we have the terms front and back. As the name implies, front is going to be the like the next thing to be served in the queue, so the front of the line, and then the back of the line, like, you know, where you enter when you're like, hey, you're like, hey, where's the back of the line? It's like all the way over there, and you go all the way over there and wait and hope, you know, Black Friday's coming in. So when your Black Friday comes in and you need to study for your test and you're looking at those lines, well, you know, don't get COVID or anything, but if you're looking at those lines, you know, think about your Q and DQ, and you can say that you were studying for your test. That's why you went to wait in line to buy a GPU or something. Okay, but yeah, so you got your DQ and your NQ, and front and back. One other term that you might see, this is more of a stack term, but I'm still going to mention it, and then it'll make more sense with the stack, why that's called that way, is top. But top really is kind of the same thing as front. And another term you might see is the word peak. This one's not really a pure version of a queue, but peek is like when you're peeking to see what's in the line. Because technically speaking, the queue is like this mystery box. You can't see it. And you can NQ stuff into your mystery box, and you can DQ stuff, but you can't see what's in it. Peek allows you to see what's in it. So like, you can only see the front of the line, like who's next, because you can service them. It's like, imagine you're like the cash register, and you can't see who's in the line or how many people are there. All you can do is say next, and then whoever comes out is going to be who you get to serve. Peek allows you to do that. Allows you to kind of peek in and see how big the line is, or like who's second in line and things like that. But again, they're not pure versions of what a queue is in the simplest terms. That's all the terms that I can think of. We'll see if something comes up, but yeah. Okay. Just to really drive this home, think of this as a queue. Think of this as your front and your back. And let's bring in our people. So if I say NQ something, it means insert it all the way to the front. And then technically speaking, the back is pointing. If you think of this like little pointers or arrows, they usually point at the front and the back. And the back, they might point at the actual item, the last person in the queue, or to the next available spot to kind of wait at. So when you enter the queue and you say NQ, it puts you in the back, and then it shifts the back one. Another person comes in, NQ, puts there, and shifts. Finally, let's say that we want to DQ someone. So then, oh, he got snapped out of existence. He gets served, and he goes away. And then this moves. Either that moves or the whole thing shifts forward. But that's not what we care about. This is theoretical. Okay? So that's NQ and DQ. Now, as you can see, if you start thinking implementation-wise, we're going to have to store this in some form of list. The two choices are, like I said, linked list or arrays. Let's talk about the pros and cons of doing each one. Actually, before I do that, let's talk about how we would do that, because it might not be so obvious. So let's do that. Which one to start with, array or linked list? I'm going to go with linked list, because that's the one that I'm going to show you, and that's the one that I think your assignment is on. So I might as well do that one first. So with the linked list, this is really nice, because here's the thing. If you notice so far, from what I've talked about, I have not talked about things like size, how much people are in the queue, you know, is it always going to be full? Is it going to keep growing? I haven't talked about any of those things. And that's because you might not know. And that's going to be a problem with arrays, because we know that arrays are fixed size. Sure, we can use a vector, but normally arrays are fixed. So from that implementation point of view, that's an issue, right? Because what happens if we need more space? It's like Disneyland, you know, they got to have like an overflow lane, basically. So those are all things that are going to come into play in a minute here. But fortunately for a linked list, you don't even need to make a double linked list to implement a queue, by the way. In fact, I would say it's overkill and completely unnecessary. When you make a linked list, I'm going to show you the right way to do it first, and then I'm going to show you the wrong way. Okay? So when you got yourself a linked list, you usually have a head pointer. And as we saw last time, you could have a tail pointer, whether or not it's a single or double, except I just showed it to you with double, but you could have it with a single as well. So if you have something like this, you have your head and tail, and you got a linked list you're building as a queue, where do you insert? And again, don't worry, I am going to be coding this next class. I'm just not coding today because I'd rather just show you the concepts, okay? It's harder concept and code, it just really slows on the pace. So if I'm trying to insert here, the right way to insert is rename your head to think of that as the, sorry, I'm processing, front of the queue, okay? And rename the tail to be the back of the queue. Now, the reason I had to stop for a second is the same reason that you have to be careful. The way this looks is misleading because like the arrows, you know, when I think of waiting in a line, like if I'm drawing somebody waiting in the line, I usually have them face the front of the line, right? So when you're looking at the pointers from the linked list, you know, in our heads, it makes more sense to say this is the front and this is the back because of the way the arrows are at. But there's a major issue if you do it the other way around. That's the bad way. This is the good way. So I'll explain that, okay? But first, let's just keep going with this. So if you do it this way, and you need to insert something into the front, or sorry, no, if you need to insert something into the back, because you never insert at the front, that would be cutting, then it's very easy. You know, if you make your node, and this is someone that's going to enter the line, they go to the back. Well, that's very easy. You have a pointer that points to the back right now, and that pointer is called B. So if I go in and I want to put that in there, all I got to do is get the back pointer's address, which I have in B, and then make B next, basically, make that point to here, right? To the new item that I'm inserting. And then just make sure you update the back pointer to always point to the back, so that like the next person coming in knows where the back of the line is, right? Okay, that's how you enqueue something. And then to dequeue, as you put dequeue, if you just have to get the next person at the front. The next person at the front is going to be right here, right? So all you got to do is just basically take him out. And I don't mean like take him out, like you just get him out of the line and serve him, basically. Okay? So, bam, you go do something to it. And then you want to make sure that you move the front to be the next item there. So from a programming perspective, really what you do is you are going to create a temporary pointer, you know, called temp, make it point to the item, then update front to be the second thing, and then go ahead and actually, you know, get the data value of that, return that, and then deallocate this, which basically gets to go away. That's another thing that I want to bring up that I didn't mention. A queue on the pure version of it is, you know, the two operations to enqueue creates something that gets inserted into the queue, right? Dequeue, on the other hand, is a destructive operation in the sense that when you dequeue something, it's like it has to get out of the line and do whatever it has to do because then it's going to go away. There's no way to like access something at the front but not delete it. It's like, here's a line, and when you say next, the person coming out of the line at the front is going to come out of the line. He can't go back in there. Once he comes out, you got to do whatever you got to do, and then he's got to go away. You can't like go back to the front because all the people in line will be like, oh, what is happening, kind of thing. Okay? So from the linked list point of view, what that's saying is, once you take it out, you can't just put it back in. Okay? And as it's implemented, you really can't unless you do a slow operation. So that's basically how you would implement it in the linked list. Now, let me tell you why doing it the other way is bad. So suppose that you go with the intuitive, for me it's intuitive to put the arrows in this direction and then like put the B and F like that, right? So the front is there and the back is there. And you're like, I would like to insert something into the queue, into this version of my queue. That's no problem, it's doable. It's like inserting at the beginning of a linked list. You just get the head pointer, which is B in this case. So all I go is and say, okay, this is something called temp. I'm going to assign temp next, which is that pointer, to point there. And then I'm just going to assign B to be whatever temp is, which makes it point there. And bam, I am able to insert into my queue without problems. I'm also able to remove one item from the queue without problem. So if I say next person in line, oh cool, let me just take this out and then make sure before I take it out. Well, not as much I can do, I can take it out. But now what? This thing's pointing to nowhere and I want it to point to here. But how do I make it go back? I can't because it's a singly linked list. The only way I can do that is if I go and get the B pointer here, traverse the entire list using a loop, get to the next last item, and then make that be F. That traversing through the entire linked list is going to take time. How long is that going to take? Well, it's going to take n time, where n is equal to the size of the current queue. So if there's 100 items, I have to go through 100 pointers, which takes time to be able to update that front. Not very efficient. In fact, from a time complexity point of view, we call that O of n. Don't worry too much about this stuff. Again, this is 302 land. I'm not going to test you on this O of n stuff. But the other method that we had here is always instant because there's no traversal required. So we call that O of 1 or O of constant because it's a constant amount of time every single time. Doesn't matter how big the list is. I think without even understanding 302, you can appreciate how the top method is faster than the bottom method because this method is dependent upon the size of the list and the fact that you have to go through the entire list. The top method, it's immediate. Doesn't matter how fast the list is. It always takes the same amount of time and it's immediate. So like that's always better than anything. It's like you have two options. One option is like I gotta walk to school, and the other option is I can just teleport. Well, just teleport. Bam, you're there, right? So that is why you want to implement a queue as a top version. Okay, so I don't think you are going to. Well, I don't know. I don't know what the assignment PDF says, but I don't think you get punished for implementing it in an inefficient way. But definitely when you get to 302, you have to understand why something like this is inefficient and why you shouldn't do it. Because, now you start to care about doing not just getting something working, but actually working in the best way possible. So that's how you would implement it on a linked list. Again, if this is still not making full sense, it will when I code it as a linked list. But let's go ahead and move on to how you would implement this in an array format. So again, I'm going to go ahead and start. In this case, I'm going to start the wrong way to do it, and then I'll show you the right way. So with an array, the first thing you're going to have to think about is the fact that you need to make the array of a fixed size, which is good as long as you know how big the queue is going to get. If the queue is only going to be 5 items, you can make your array of size 5, and you're okay, right? As long as there's never more than 5 items in the queue at once. It's like when you're trying to do a line, right? Like you got a business and you're trying to put some space for lines when you're designing your grocery store you're going to build. You have to decide how much space you want to leave for people to wait in line before they pay. That's a decision you got to make at that time. And if you screw it up and you completely predict that as you're like, oh, worst case scenario, rush hour, there's gonna be 6 people waiting in line. Turns out that there's 20 people because your shop is super popular. Where are 20 people gonna fit? They're gonna probably wait around. You ever go to the gas stations where there's a line and the line goes around the entire gas station's hallway, and it's oh gosh, this is gonna take forever kind of thing. Yeah, that's kind of what you don't want to happen here, especially because at some point with an array, you are going to run out of size, and you can't just improvise extra line areas. It's just going to segfault or go because you're going to go out of bounds or something, right? Of course, what you can do is you can resize, and that is something that you can definitely think about. If you're okay, I think I'm going to be okay with this size, but I want that flexibility, you can always resize. So you can definitely add resize as one of the things here, but that's really specific to an implementation. That's why I didn't put it there. Okay, so with the concept of resizing in mind, even with that said, let's see if we can still maximize the usage of space, because that's the other thing. So again, I'm going to do it the naive way here and show you why that's wrong, and then show you the solution. So we have an array, and this array holds 6 items. And again, we are going to have a front and back. So I'm going to start out and say that my front is here and my back is just here. Actually, let me do arrows. I'm tired, a lot of talking today. Okay, bring my people. I like how I'm using stick figures today. I don't know why. I mean, I know how it came to be, but I was not expecting that to be the case. But I kind of like it. You know, forget numbers and letters for one day for once. Okay, so let's go ahead and insert him into the line. He's kind of big. We need to shrink them a little bit. There we go. Okay. So, you know, he's going to go in. He goes in there. Very cool. We got someone in our line. And then already there we kind of like stuck because we want to insert somebody else. It's like, what do we do here? Well, okay. That failed. So maybe now let's try to make the back go this way. So it grows this way. Okay, that's going to work. So we want to insert somebody else into the line. We just put him here. And then every time we just +1 the back, right? Okay, this is working pretty well. We want to put somebody else in. Sure, that works. And technically, this is going to work all the way until we run out of space. Which, if we don't expect to, then we're okay. All right, let's say that finally the line starts moving. So this person gets out of the line. So he jumps out. Okay. This has to move to point to front. Okay? That's one way to do it. All right, I hope already there you're starting to see like red flag kind of thing. All right, so you get one more person in the line. I guess I forgot if I was pointing to the last one or the next one. Let's point to the next empty spot. And then this person gets out of the line. This moves back. And then one more person comes into the line. This moves back. And then one person gets out of the line. And then one more person comes to the line. And then it's like, sorry, line is full, so you either don't let them enter the queue because it's full, or you resize it. But here's an issue with either one. You have empty space available. Like you have all this space right here. So this is bad. This is, like I said, this is the bad example. Because like, you plan to have, okay, you know, there's never going to be more than 6 people in my line. But the way you implemented this, at least coding-wise, like you're wasting space once somebody leaves. So that fails. So then you're like, okay, fine, this method failed. So what do I do instead? Okay, every time somebody leaves the line, let's just shift everybody forward, which is, I guess, kind of real world like, because that's what actually happens in the line, you know, when somebody gets served, the entire line moves forward. And that kind of just happens as like flow of life, whatever. So like, for example, yeah, you're in this situation here, and then like this person gets out of the line. So then what you do is you basically shift them all forward by 1 and so on. That will work and that will maximize your space, but let's think a little bit about this whole time complexity situation. Moving things in an array is an expensive operation. You know, in the worst case scenario here, because that's always something we like to look at when we're looking at algorithms, is worst case scenarios. Let's say you're something like this, and then this person gets out. You gotta shift every single person here. So you're gonna have to put a for loop that's gonna move that, and you're gonna move that, you're gonna move that, move that, move that. That's a lot of people. How many moves is that? That's gonna be, if n is the size of the array, it's going to be probably n-1, right? Because you don't, there's one person you don't move because it's the front because he gets out. So that's long. And you got to do that every single time somebody leaves the queue. Again, that takes time. It's not instant, right? We already saw with the linked list that you can make this into an instant version with the version on the top there. It's more like this version here, what we're doing right now. So sure, this happens only after the person leaves the line, which is why this works in the real world, because what ends up happening is while this person leaves the line, the entire line moves forward, right? But think about like from a traffic perspective, right? Like when there's traffic and the guy that slows down, or a person slows down in the highway and like slows down traffic, even if they just slow down for a second and accelerate, that kind of, you know, it's like a wave that like goes through and like spreads all over the highway and slows down traffic like a mile behind, right? And there's no way to kind of fix that. And that's just the way it works, right? So this is not the best way because there's a better way to do this that avoids this problem, right? So we have a comment. I feel like if you use arrays, they should always be full and dynamic, so space isn't being wasted. So that's if you're going on to, remember space and time thing? That's if you're going like for like my space is like the most valuable asset part, but not for time, because here's the issue with time. You got to do this thing when you got to shift everybody. Or actually, no, in your case, because you're saying that it's always full, every time you insert something, you have to make a brand new array. You have to copy everything over from the old one and then make it +1 bigger. And that's actually going to waste more space too, because when you're copying it over, you need to first allocate the new array. So that means you have ×2 the size, copy things over, and then you can deallocate this. So that's not efficient. The linked list version, though, that never has any extra space. The only sacrifice you're making is that instead of storing just the data, you have to store the data +1 pointer, right? Well, +1 pointer per data point, and then plus the 2 pointers for front and back. So if you have 100 items, you need to store 102 pointers, right? You have to store the 100 items with the 100 pointers, and then you have the 2 pointers which are front and back. So pointers themselves, sure, if you're storing integers, it's like not that cool, but if you're storing like lots of data in there, the pointers themselves are only going to be the size of the addressing system, which is probably 4 bytes. 8 bytes if like you're using some fancy system. So whereas like if each block of data is like one megabyte of data, then you have 100 of these. At most, you're going to have like 101 megabytes, including the pointers probably. Whereas like with the array version, when you're copying the data over, because it's already full with 100, then it's going to be 200 that you need for temporary while you're copying over, and then you can deallocate and go back to having 100. So don't be so quick to say that the array version is faster. But I do like that was brought up though. Okay, so if this failed, how do we optimize the array version so that we don't have to do all this moving around? Because we are able to achieve O of 1 for insertion for NQ and DQ with the array version. It's just not this way. We can't fix the size issue. For that, we just have to hopefully not have to every time we add things in there. We just kind of make it grow, like double it each time, or predict and whatnot. But we can definitely fix the issue with the shifting. What we're going to do is we are going to. I wish there was a cooler way to show this, but there really isn't. Maybe I can. Let's see. I heard my dog outside. I think my dog's outside. Okay. Yeah, I can't show you the cool way of doing this, but I can show you with my hands. No, I have an idea. Hold on. Yeah. All right, prop. This is your array, beginning and end. How do we fix this array so that we don't have this issue? Is we turn it into a circle, and that's all we got to do. Okay. So that was my little 5-second prop. Okay. So what we're going to do is I'm going to first draw it as a circle, but obviously you can't make a circle in like coding. But it'll be basically what it represents, okay? So, hopefully you guys can hear voices. I apologize if you hear voices. Okay? So, this is going to be the exact same array. All right? So we got 0, 1, 2, 3, 4, 5. Well, okay. Maybe we'll make it slightly bigger because I made it slightly bigger. 6 and 7. Okay. All right. Now it's the exact same array. Okay. What was the issue with the array queue again? The issue with the array queue is that you don't have a way of optimizing insertion because you either have a gap at the beginning or at the end, and the only other way to fix it is to keep shifting things forward, which is not good. Okay. So if we do it this way, and we got our stick figures, let's just make a bunch of them. There we go. We're going to need more because we have more spots. Okay, so it's Disneyland here or something. I don't know. So we still go ahead and start with our front and back. So I'm going to say this is front and this is back. And we'll just say we're actually, you know what? I'll put them in the inside of the circle. All right. So front and back are right there. We get someone into the line. All right. And then we are going to go ahead and put back to the next available spot, which is that. And then we're going to keep inserting a couple of things, it's like this is before opening time, so the line is growing, but it's not flowing yet. It's like when you go to like the DMB or something. And finally, the line's gonna start moving, okay? The DMB people finally opened up. So you get him out of the queue, and then this moves forward. Okay? So now, all is good. You can keep going. So more people get into the line because they're like, oh, the line is moving. Let's everybody jump in the line. So they all get hyped and get into the line. And then one more person progresses, gets out. And then maybe one more person progresses and gets out. And here's the beauty of this circle. Let's say one more. Oh, I forgot to move the B. Not the B's over here. Or technically it's here because it's next available spot, right? So now one more person goes into the line. Well, it's a circle, so they just go to the back because there's a space right there. You see that? So whereas before we would have ran out of space and we would have been able to fill it, now we're able to fill it. In fact, you can keep filling it and you still are able to easily keep track of where the front is. Now, this is easy to see because I have it as a circle, but this is still going to be implemented as a flat array. So you're still implementing this version right here. Here's all you got to do for that. It's a little trick. You're using modulus for this. So as the line fills up and the back keeps moving, let's say this person gets out, gets moving, and then this person gets out, and this moves, and then more people come in. Well, here, hold on. All right, so we're here. So one more person is going to come in. So now when he comes in, the back, instead of pointing to the void of nothingness, it goes back to the beginning and points to there. So then the next person that gets in the line goes there. And then if one person gets served, comes out. And then let's say that another person gets served, comes out. And then let's say that a couple more people come in. Put him here. This should move back. Put him there. And you could even have like a situation where it's full. And like these, they look like they're next to each other, but they're not. Because we know where the front is and where the back is. Now, if one more person comes in, now you have a problem. Now you got to actually make a brand new queue, dequeue everything, blah, 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 and then add it to the new one. And then you're good. You can't just like copy this exact ordering into a bigger array because it'll break it. It'll break the sizing. And I'll show you that when we code it. But it'll break the sizing if you just copy. You have to literally like dequeue everything out of one and then queue it into the new bigger array instead of just trying to do like a for loop that copies it over. That will break it. So how's the trick? What is the trick to be able to do this from a coding perspective? Very simple. When you know that you keep the size of the array somewhere. So we'll say S. S has in this case S has the value of 8 in it, right? Because it's the size of the array. So you keep increasing F plus 1 every time you add something to it. And whenever F is basically equal to the size, then just reset it to 0. That's one way to do it. An even nicer and more kind of cooler way is just go ahead and do modulus on the value of F. So every time you increase F by 1, go ahead and just do mod on that. And then if the modulus of that goes back to 0, do the modulus on the size. So S. If that goes to 0, because like when you're saying, if F is 7, 7 mod 8 is still 7, right? But if you do 8, 8 mod 8 is 0, right? If you have like 20 mod 8, what is that? 4? So it's 4, well, because we're counting from 0. Yeah, I think it's 4. So if you do that, then it means it must wrap around to the 4. So using modulus, you can just do this little trick. It's very simple, one line of code, and you have this. Now this has a special name, and it's called a circular queue. And so doing this method, you have optimized it so you never have to shift things around. So you have that O of 1 constant time insertion time or enqueue time and dequeue time. You have made it as fast as the linked list. The only catch is that with the linked list, you can just keep allocating memory on the fly. In this version, you have to allocate it ahead of time because it's an array. And you do have that cost of time to be able to resize it and copy data over. So the circular queue still has its downside compared to the linked list version, but it's still an important thing to understand. And so that is why we covered it. Okay, so now I've shown you the best ways of implementing either a stack, either a queue in either a linked list or a All right. Questions so far? We're halfway there now. That's all that I have for Q, so we can move on to stacks. Water while you guys ask questions. All right. I guess no questions. Cool. Like this stuff is not rocket science. It's don't think this is how 302 runs. This is how the beginning of 302 runs. Yeah, it's a nice algorithm. So, yep. And it's very easy. Like I said, we'll code it. And there's already code, by the way, on Canvas from previous semester. I think I coded it. So you can find that up there already if you're curious. In fact, there's probably already code for the linkless version as well. But like I like to code it from scratch every time. It keeps me awake. Okay. Like I said, we have tons of time, so even if we don't finish stack today, we're good. But we probably will for the most part. All right, so that's one of them. So the other one is stack. So remember this acronym that I said that a queue is a first in, first out system? It turns out that a stack is going to be a last in, first out system. And I'll give you some examples of what this means. What it means is that the last person that gets in the line is the first person to always go. So like it's like literally a line where like every single person cuts the line. A better example, one that's a little bit outdated, but who knows, maybe it's still used in some stores, is think about like a refrigerator. Or not a refrigerator, but like just think about a grocery store, since that seems to be the theme of it. Oh, no. I have a better one. This is one that somebody brought up at some point one semester, and I was like, damn, this is amazing. I'm going to use this forever. And it just came back. So a little bit outdated now because of COVID, but still. Okay, so we're in Las Vegas, and so one of the popular things here is, of course, the buffets, right? At least for the tourists. Although I will not deny it, I was a fan of buffets as well. Before the dark times, where not buffets closed and everything. And so in buffets, usually what you do is you go in the buffet and you get food, right? And before you get the food, you go and grab a plate. And so those plates are usually, at least in the buffets, some of the buffets that I went to, they're usually in some it looks like a trash can, but like it's not a trash can obviously, but like there's a spring and they dispense the plates, right? And if we have somebody here that works in the hospitality industry and can provide us with a name of what these things are called, that would be greatly appreciated. Otherwise, I'm just going to call them like trash cans that give you plates, but they're clean. Okay? So, so basically the way they work is they just have a spring, and that spring pushes the plates up, right? And so when a person comes in to grab a plate, so where are our people? Our army of stick figures. It's like, oh no, we cut off the head of one of them. 2 more shall take their place. Okay? Yeah, they multiplied. All right, so we got our buffet. Plate dispenser. Yeah, that probably sounds legit. Although I was expecting more exciting of a name. I don't know, like some Vegas sounding name. But yeah, that actually sounds about right. So yeah, because the pest dispensers are those little candy things, and I think they work the same way. So yeah. All right. So yeah, so you come to the buffet and you grab a plate, and then you go and eat, right? And then the spring pushes the plates up, basically. So there's always a plate on top. But now here's the catch. One of our workers at the buffet is bringing in a stack of new clean plates. And when he comes in, he goes in there and he drops them at the top. That way, the customers are always getting the freshest plates per se. The ones that have just been cleaned the most recently and are probably still warm from the cleaning washing device. Okay? And it pushes down the other plates. And this is great because then you come in and you're like, oh, nice and warm plate. Yes, very clean, happy plate. Okay? And same other person comes in and grabs their plate, and then they go. And then another, eventually the plates start going out, and then you're like, oh, I should replace the plates, 'cause you're a very good worker. You're like keeping track of that. You go in there and you replace the plates. And here's one I don't know if it's an issue per se, but one situation that could happen here. The plates at the bottom are the ones that are going to remain the longest, right? At some point they were super fresh, but like other fresher plates came along, and so the plates here have been idle all day. All right? Now I bet you'd probably they empty them at night or something, but let's just say they didn't. All right? Let's say that budget cuts. We can't wash our plates multiple times. It's been washed, it's not been touched by anybody, it's okay. Plus, you're doing such an amazing job that they never get to that plate anyways. That plate's been there since like 1965 or something. All right? But guess what? One day, relevant to the top. Well, no, I don't want to say that. Okay, let's just say one day you get sick, but it's not COVID because I don't want to say you got. Let's say you get sick, you get, I don't know, you just eat something that makes you sick, okay? So you're sick that day, so you don't get to go to work. And then the person that subs you in, it's like last minute, that's not his job. His job is maybe he's cooking or something. But, he's trying to help you out, because you're sick, so he's trying to cover for you. So, he's busy doing other things. So, the plates, he's still replacing them. But because he's not as active, they start to kind of eventually wind down. And finally, they almost get empty, and you start getting into the plates that have been there for a couple of years. And finally, somebody grabs it, the last plate. They go in, they grab the plate, they eat, and then they die from like food poisoning because the plate was there for so many decades. Okay? Bam. That's not good, right? That's bad. Sort of. End of story. So that's how stacks work. Basically, the idea of a stack is that you want to feed the latest thing, and for some systems like this dispenser, it's actually a good thing because you want the customer to have the freshest plate. And then, of course, to avoid this issue, you probably clean them up at the end of the day anyways, right? So if you were using a queue system, first of all, you'd have to have a different design of a dispenser unless you have a way of accessing from underneath. And then you would also need to, you would have to make the decision that like the oldest plate will be fed first, which means that by the time if this thing is big enough, by the time the customer always gets the plate, it's going to be cold. It's going to be room temperature because they're the place that's been there the longest. And so that's just one example of stacks that somebody thought up and seems kind of useful. Okay? So anyways, now that I told you how stacks are, let me just give you the terminology and then the implementation of how we're going to implement our plate dispenser in the computer next class. Okay? So first of all, just like any algorithm, like I said, that we look at, we care about the insertion, the deletion, and the access time. So for a stack, we have a special name for inserting into the stack and for removing from the stack. And for insertion, it is called push. So you push into the stack, that's inserting. To remove from the stack, basically, again, just like with DQ, it is a destructive operation. Once you take it out, it's a use it or lose it kind of thing. It's like when you grab a plate from the plate dispenser, even if you don't want to use it, you're not supposed to put it back because you contaminated it with your hands, right? So like you're supposed to like just if you grab it and you end up not wanting to eat, you just take it to your table and just leave it there, and they'll take it away, right? You're not supposed to be like, oh, I didn't use this, let me go ahead and put it back. No, that's like a violation of some sanitation rules in OSHA or whatever. So that's the same thing with pop. Once you take it out, you can't put it back in. So that's your delete/access. In addition to that, you still have the other terms that I did mention before. So you have your top and peak. Top, in this case, is going to be what is the next thing to be removed. And again, the peak is that ability to be able to see, like, it's like if you wanted to see, like, oh, how many plates are underneath? Or like, what's the plate underneath like? It's like, you're like, oh, that plate on the top looks nasty. Can I grab the one beneath it? Technically speaking, with peak, you could do these kind of things. But again, they're not the pure version. The pure version is like, here's your plate dispenser. You either grab the top plate or you don't. But don't do anything else. Okay? So push and pop, top and peak. And That's pretty much all the terminology there is. It's kind of the equivalent to front and back. It's just going to be top. This is like your front in the queue, okay? Kind of. All right, but I'll delete it because I don't want to confuse you with the word front. Okay, so let's just do a practice with people. Let's stick with the people system. Let's just make a stack and just throw some things in just to make sure that we're on the same page. So usually to represent the stack, you can draw a rectangle, but I like to do it vertical. And then you just insert. So for example, if you want to push something into the stack, you go here and you put it in, right? So that's pushing. Let's say you push something else into the stack. Because it's the last item in is the first one out, it goes to the top. And so over here, you keep track of what's the top. So as you insert something into your stack, you move it up. Okay, so you always keep track of what's the top. Let's push one more thing in. Keep track that that's your top. You don't really need to keep track of what's the bottom of the stack because that's just usually just the beginning of the array or the beginning of the linked list, whatever it is. You don't need to worry about that. Let's say you pop something out of the stack. So when you pop something out of the stack, you remove the top. So that's the last thing that you inserted. It's what comes out. And then your top moves down to the next available thing. Let's say you pop again. Comes out of the stack, move that down. Let's say you push things in. All right, put that in, move it up, push again, put it in, and so on. That's pretty much all there's to it. Just like with the array version of this queue, if you run out of space, you're going to have to resize. But here, it's actually really nice because you don't have to do the whole dequeue and requeue situation. You don't need to pop and push everything out. All you got to do is just literally do a for loop that copies it over, and you'll be good to go. But again, that's something that I'll show you coding-wise later on. Okay, let's go ahead. And since we're still fresh with the array version of the queues, let me show you the array version of the stack first, and then we'll do the linked list version. Okay. So there is no circular stack situation. That's only for queues. That is not a rectangle. Come on. There we go. Okay, here we go. All right, and so let's go ahead and mark what the top is. So I recommend you keep the top as what the actual item is. So in this case, the top starts at -1. And then as you insert things, you are going to increase that. And here's a nice little cool thing about the top. The top is also the size of your stack. So if you want to know what the size of the stack is, just see what the index of top is. So right now, well, I stand corrected. You have to +1 it if you're counting from 0, because here you have actually one item and the top would say 0. So +1 it. My bad. Okay. Unless of course you have the top pointing to the next available spot, which I don't think that's common. All right. So as you insert things into your stack, it fills it up very nicely. And you don't have the issue when you remove things, because when you pop things, it goes back this way. So you never have a situation where, like with the queue, where you have a gap in the beginning and that's why you had to shift things. That never happens with a stack. Therefore, you never have to worry about that. And also, from an asymptotic complexity point of view, inserting something into a stack, so push and pop are both instant. They're constant time. There are no end times involved. The only time that there's an end time involved is because you have to resize. So like, for example, let's say that you're very push happy. So you push, and then you finally push this one in. Oh no, you decapitated him. There we go. And now your top, you're pointing there, and then you try to push something else, then you're out of size. So you make a new one. But again, like I said, unlike the queue where you have to actually dequeue everything and requeue it in order, here it's just a matter of literally duplicating it. So like, copy this over into the bigger array. Don't make it +1, at least double the size, but then you're good to go. So it doesn't matter from a time complexity perspective whether you have to dequeue and requeue or just do a for loop to copy. They both are considered to take n time because you're copying the entire list and it's being the size of the existing array. So they're both just as bad. But then again, there's nothing better that you can do, because when you resize, you have to copy the data over. So there's no way around that. That's really all there's to it with the array version. The stack is very, very easy to do, as long as you don't screw up the top. One of the things is make sure that that you keep track of that when the stack or queue are empty, that you don't try to remove an item from either of them, because you could segfault. So you're gonna put an if statement that checks whether the top is -1 index. That means that it's empty. Or in the case of the queue, one way that you can figure out whether something is empty is if F and B, the front and the back, are pointing to the same thing. If that is the case, and your back is supposed to point to the next available spot, then that means that either the queue is empty or full too. But you can keep track of that, because when you insert, you would see that it moves, and then you can flag that. So those are the two ways to keep track. But again, those are implementation details that we'll get to see when we actually code it. Those are the things you don't think about right now, but you kind of need to know when you code it, because you have to make a decision on how you decide that. Make a decision on how you decide that. Weird choice of words. Okay. We are on track. We got 15 minutes, and we just had to talk about the linked list version of this. Very cool. So how do we implement a stack with a linked list? Very simple, but again, you have to be careful about what you consider to be kind of like the front or top of the stack, because just like with the queue, if you do it backwards, then you're going to run into problems, right? So let me show you the wrong way of doing it. Let's say you go ahead and say, well, I'm going to think of that as a top. And then, of course, I have my head pointer for this. If you do this at the top, if you want to push something there, that's not a problem. You just do the top and then do the top N, top next. That gets you this pointer right here. So then you can just put in there the temp, which is probably just the node that you're creating. That's the equivalent of just putting it there. Sure, no problem there. You can keep pushing all the way you want and keep inserting. But the problem is when you pop, right? So you have the same issues you have with the DQ. When you pop, you can remove it, but then you need to update this to point to here, which means you gotta traverse the entire thing, find out what the next last item is, and then shift this by 1. Not efficient, right? So just like with the queue, you don't want that to be the way you do that. There, you want to flip around the front and back. So in this case, the top is your head pointer, which is cool, because it means you don't actually need a tail pointer in a stack. You just need one single pointer. With the queue, you need the front and back. So you need the head and tail. With this, you just need the head, which we call tail, or sorry, top. So it's a little bit weird with naming convention. So yeah, if you do it this way, then inserting into your stack, so pushing into the stack, let's say this is called temp. It's a matter of saying, okay, I would like temp next to be equal to whatever the top currently is. What that is doing is that is basically making this pointer point there. So that's good, because that is basically saying that we are going to put that in the beginning. Okay. The second thing we want now is to just update what the new top is. So the top, it would just make it say something like T gets temp. So just another line of code to just basically update that. And then bam, that's how you push. How do you pop? Well, the reverse. So you go ahead and make a pointer that points to what you're removing. And then go ahead and do temp next gets T, so that you can update the top to be the second item, because it's going to be the new top after you remove it. And now it's just a matter of deallocating this and returning the value from the function. So very, very straightforward. Again, you'll get to see the code when I do it next class, but that's how you implement it. Just like with the queue, the stack has best of both worlds. It allows you to keep inserting things until you run out of memory on your computer. And it is fast, like O of 1 for insertion, deletion, and access. So basically for your push and pop in the case of a stack, or with a queue with the NQ and DQ. So yeah, like I said, I could have covered stack and queues in 5 seconds, not 5 seconds, 5 minutes, but I'm trying to give you the foundations of how you code this, so that next time we code it. And the final project is going to be, I believe, implementing these two algorithms. So You want to make sure you get them. Also, they're very fundamental. Like literally today in my Trio 2 class, I was talking about the breadth first search algorithm and depth first search algorithm, which is how you traverse graphs. And it turns out that you actually use a stack and a queue as part of those algorithms. So this is something that you get to use for a lot of times. A stack is like super important for a computer. Like when you make a function call, and what you're doing for recursion is you're adding your function call to a call stack. And it's a stack because that way, it knows that the last function is the one that needs to finish first and then go to the one that called it, which is actually the next thing in the stack. So stacks are very fundamental for memory usage and things like call stack. And in general, memory itself, when we say the stack and the heap of memory, I believe I use those terms at some point this semester, stack and heap, how those grow. They're growing like a stack because you just push to the next available spot. Same this one, you push to the next available spot, right? And when you stop using it, you remove it. So they're growing like a stack. We just can't call them both stacks. So we call them stack and heap, but they're both using the stack data structure. What other usages of stacks? Of course, queues, I don't need to explain to you why they're important. I mean, everything in a computer that you need to organize and give priority in terms of wait time, you have multiple processes trying to use the CPU. If you want to allow, one thing, the first one that requests the CPU to be the first one that uses it, you make a queue out of that. So they wait, so that you have scheduling going on. And you'll talk about that in your 370 class. So stacks and queues are like the heart of a computer, and you'll get to see them in a lot of usages. So not the first time you'll see them probably today, and definitely not the last time you see them. Okay? So any questions now? Do you have anything? Tired from all that speaking. Hopefully you all got stacks and queues. Like I said, the plan is today we finish this. Next time we code it on Monday, and then if we finish coding it we have basically a full week to code it. We can take 2 days if we need to. If not, we'll just do it in 1 day, and then we have the review day. If otherwise, we have 2 review days, so we'll have to figure out. But we won't have class on Wednesday of December 1st, because that would be like 3 review days. That's just too much. All right then, great. So hopefully now you are prepared to be able to do the assignments. Can you go over the linked list stack method again? Well, you can still get the points on. We still got basically 3 days of lecture time that we're gonna have. So that's 3 days of lecture. So you can get points then and redeem them then. So yes. As for the question on the linked list version of the stack, let's just scroll down there. Here we go. So again, it's just like a normal linked list. The top is your head, and that's where you insert, and that's also where you pop. Just do not use the tail of the linked list to insert and remove. All right then. Well, I'll be at UNLV tomorrow. In case anybody needs anything in person urgently, I'll be there. Other than that, I hope you all have a good weekend. We're so close to the end of the semester, so make sure you all get your assignments done and everything. I don't know if there's some sort of event, but Thanksgiving is next week, so if there's an event, it's probably not happening tomorrow. I gotta go tomorrow to do a presentation on something else, and also to do a meeting from some computer lab space, and to pick up some things that I ordered. So I'll be there all afternoon. Okay, great. Well, then, I hope that you all have a great weekend. All right? Get the assignments done early so you can have a nice Thanksgiving break and you're not stuck, doing homework on Thanksgiving. So you move the pointer up each time you add something and move it down each time something is removed. Yep. There. You don't need to have a tail pointer for a stack. So you don't even worry about it. You're literally making a linked list, a single linked list like we did like the first day. You only got to worry about the tail pointer when you're doing a queue. And like I said, I'll code it next time. So you'll get to see it coded. Great. All right then. Bye everyone. See you next time, Monday.